We all know how to find maxima and minima of functions of a single variable. It's fairly straightforward. You take y equals f of x, you compute f prime, you set it equal to 0, you find values where f prime is 0 or undefined, and then you test the second derivative to see whether it's concave up, concave down, whether it's a minimum or a maximum. And that's something we've done several times. What if you have something slightly more complicated? Suppose you have a function of two variables. Well, it's going to turn out that this time we're going to take fx of xy and set it equal to 0. We're going to take fy of xy and set it equal to 0. And when we solve this system, we should get the point AB where both fxab is 0 and fyab is 0. In other words, that's what we call a critical point. So let's see if we can do this for a specific example and then determine whether or not it's a maximum or a minimum. And there's going to be a trap that we're going to have to avoid. Let's suppose that f of xy is given by x squared plus 3y squared plus xy minus 5x minus 8y plus 9. That's just a polynomial, so the partial derivatives are fairly easy to find. Fx is just 2x plus y minus 5. Fy is simply 6y plus x minus 8. And remember, we want to set both of these equal to 0 because we need both of these first partials to be 0 simultaneously to provide us with a critical point. By the way, if you rewrite these slightly, you have 2x plus y equals 5. You have x plus 6y equals 8. And I assume you know how to solve a system of two equations in two unknowns. Just to make it slightly more convenient for you, I will go ahead and show you that's the solution that gives you both of those results. So in other words, when all is said and done, we find out that fx at 2, 1 is 0, fy at 2, 1 is 0, and if we go ahead and work out what's going to happen with the second derivatives, we find fxx, well, fxx is just a constant, that's 2, okay? And fyy is just a constant, 6. Both of those are positive, and so both of those are suggesting concave up. So it looks like f at 2, 1 is a minimum value. If you check out a contour map, you'll see that 2, 1 is in fact the lowest point. So that seems to have worked out just fine. What if we tried another example that looks similar, but turns out not to work out the same way? In this case, we have f of xy equals x squared plus 3y squared plus 4xy minus 8x minus 14y plus 15. Let's check out the first derivative. 2x plus 4y minus 8 equals 0. And fy, 6y plus 4x minus 14 equals 0. I leave it as an exercise to the student to determine that the solution is once again 2.1. 2, 1, excuse me. That's our critical point. Check it out. If you plug in 2, 1 into fx or fy, you will get 0. If you look at fxx, you get 2. If you look at fxy, fyy, you get 6. Both of these are saying concave up. So it looks like a minimum, but it's not. This is a trick problem. Let me show you the contour lines. We have the same point here at 2, 1, but this is where the function is 0. The previous function had a minimum. This one actually increases to the upper right and lower left, and it decreases. These are negative contour lines on the diagonal. And the problem is all with fxy, because fxy is 4. And I need to show you something called the discriminant. Discriminant. It's called d. It's a function of x and y, and it equals fxx at xy, fyy at xy, minus fxy squared at y. And you may be amused to consider that d is sometimes written this way: fxx, fxy, fyx, fyy. And you'll see that when you work this out, fxy and fyx are the same, so you get that expression. In our particular instance, we got the discriminant evaluated at 2, 1 is going to be 2 times 6 minus 4 squared. In other words, we're looking at 12 minus 16, negative 4. This is negative. This means you have a saddle. Okay? No matter what else is going on, this is a saddle point. In our previous problem, if we did the discriminant on this one, the discriminant at 2, 1 would have been, well, here's fx, xx, 2, here's yy, 6, and in this one, fxy was just 1, minus 1 squared. So we're looking at 12 minus 1, 11. It's positive. That means you can believe fxx and fyy. They are telling you the truth. If the discriminant comes out negative, it's a saddle, no matter what fxx and fyy tell you. If the discriminant comes out to be 0, then we just don't know. We have to try something else. And that's an introduction to using the discriminant to find the max or min of a function of 2 variables.